get started here. So how has it been better for your health? Is it not getting sick from other fellow students or just having more
No,
free time?
no, like both on Wednesday and today. I've just been on a walk during classes, and I walked 10 miles on Wednesday.
Wow.
It's going to be 10 miles today.
Awesome. That's what I should be doing too. Instead, I'm chasing after my grandkids. All right, so let's go ahead and get started here. So Ochir is up with Kali Linux. Are you set to go, Ochir?
Can you guys hear me?
Yes, faint though. Can you speak up a little bit?
Try. I'm like yelling. I'm
gonna
try use my phone. My
Okay.
microphone is so annoying. It's changing time to time. I had no idea.
But you're pretty good now.
Fine. And the other day it is not working anymore.
Yeah, I've had that same experience.
Yeah.
So, but you sound pretty good, whatever method you're using now.
Okay, I'm just yelling right now, so I'm just gonna continuously yelling.
Yes.
Because this is so weird. Okay.
So for first question, do you have a devotion?
I will try. Okay, I will try.
Okay.
Just give me a second. I'm trying to find my slideshow.
Okay, sounds great.
Here. Okay, I'm just gonna use my. Just gonna share my screen instead.
Okay.
And where is the sliding button? Okay. So hope you guys can hear me, and I'm just gonna go ahead and start. Is it okay?
Yes. You haven't shared your. I don't see your screen though.
Still?
I still see mine. Does anyone else see his slides?
Yeah, I can see his slides.
I see Isaiah 29:13.
Yeah, that is mine.
Okay.
If you guys can see that. If you guys can't hear me, I will try to use this. It's gonna be so annoying. Hold on. It's not. Nope. It's not gonna work. Okay, I'm just gonna continuously yell. So everybody can see my screen or not? If it's not, I'm gonna change it to the just screen instead of.
Go ahead. I think all the students can see it.
Okay.
Okay. Professor Lim, can you see it?
I cannot, but I've got 3 screens, so I might be looking at the wrong screen. But go ahead.
Just gonna change. Okay, hold on. I'm just gonna change to the just screen. So it's gonna be just the desktop. Should be better that way. So how about now?
Yeah, I see it. Definitely see it.
So, so as you guys already know, I'm not Christian, and I don't know I don't know about everything. So I'm just trying to give you guys a kind of devotion here. And
okay.
So what I know from my experience, what I heard, what I've seen back in my country is there's a lots of fake Christians that I know that I experienced it. So there was a lots of people that has this belief in God. They are like a kind of serving for the God kind of stuff. But at the same time, I can see them cheating on something. I can see them, doing inappropriate things. I can see them lying, and I can see them doing lots of weird stuff. And still they're saying like they're Christians or something like that. And I don't know what is that. And I hate, like in general, I just hate lots of fake stuff. Like if you are believing in something, just be truthful for that. If you're not believing in that, then you just go ahead and say, I'm not believing it, and you should just be as is. I think this devotion, I think it's called devotion, right? So this devotion kind of relates to that. So it says, because these people draw near with their mouth and honor with their lips. It's like they are honoring they're saying it is like what is they believing, but while their hearts are far from me, which indicates they are just saying it, not like heartedly, wholeheartedly believing it or confirming it. And so I don't like those kind of stuff. And as it says here, and their fear of me is commandment taught by men, say so. I think they're just fearing from the code. If it exists, if it is not, they don't care. So I just want that people, if you are like believing in something, then just be truthful to that, and that is my kind of devotion. So hope that makes sense. Okay, Kali Linux. So Kali Linux is pretty fancy image and here, but it was always not like this. So I want to go through the history a little bit. So in the beginning, so there was usually main two branch of the Linux. One is Linux and one is the Unix. And from the Unix, there's a Debian came out around 1993. And from that, at the time, the Debian wasn't like it is just a full-scale operating system. But at some point, people wanted to have this kind of live CD, live USB concept. So those kind of things started with this Nopix live CD starting with the 2000s. So I will go through this live CD in the next slide and just a history perspective. So Nopix founded at like 2000. And starting from the Nopix, there was different branches came out, which was like a security tools. So security tools being in the live CD or live USB was really helpful. And from this Vopix, there was a VAX, and those are for the like a security collection. And this is the main reason it being the security collection is like it can check the computer's health. It can do some. It has this some kind of tools that can access to the computer and fix it, or it can do. It has some tools that can access to the network and go through it. And it was initially started with just the security tools, and after that, these are three things: Vopix and Auditor Security Collection branch merged together into the Backtrack. So I think around like 2000 something, Backtrack became really popular because the people that the kids that they know Backtrack considered as a hacker at the time when I was really young. So people that started talking about this, hacking stuff and the movies. The kids has this, glass and stuff like that. They considered as a hacker, and being like a hacker and called being a hacker wasn't cool thing back in my small child days. And the Backtrack, I heard that like a long time ago, and it was just a kind of interesting thing. And when you have this Backtrack on your CD, and when you're able to load that CD from your computer, from any computer, and logging into this VP protected network was crazy, and it was like cool. So Backtrack was that, and after that, Backtrack. Where's my another slide? Okay. After that Backtrack, it became the Kali Linux itself. So I want to talk about the Live CD. So Live CD is kind of like an on-to-go operating system. So when you want, when you don't want to have any kind of track left on the system that you're using, so then you have to have something to boot. And the Live CD, it says Live CD itself can boot complete operating system from these kind of CD, like a writable media or just a USB stick. So for the first and all those non-Linux was this FM Towers operating system released in 1989, and the first Linux-based Live CD was this long-named one released around 1992. So it is just loads everything into the memory temporarily, and it doesn't it uses this some of the memory as in root file system on the memory, and it runs from there. So I think the other slide other presenter, I forgot the name, but other presenter talked about this a little bit. So yeah, it just loads whole complete operating system from this small CD or USB stick. And so yeah, like instead of booting from hard drive, so modern computer BIOS can load anything from the USB controller or CD-ROM controller, and it is really nice. And when it when you have this on the CD-ROM, obviously you can't write to it, and on the USB live CDs, you can actually use that as a partition, or you can access some of the USB partition as in storage, something like that. It is possible. And one of the biggest perks that I used a lot was just to access the computer without getting noticed. So when you boot from the CD, and then you can load your hard drives or anything that is connected to the computer. So it was like possible to go through somebody's files without letting knowing. And Live CD was crazy at the moment. And Live CD can contain lots of tools and stuff like that, and we're going to talk about that later. And basically, Live CD has this bootloader, and from the bootloader, it can load complete operating systems. And even nowadays, there's lots of operating systems that can be loaded from the USB or CD. So why is the Kali is very popular, and why it is getting popularized? So you can bring everything that you need on the USB stick. You can pre-build everything into one USB stick, and you can bring this with you every time. And it leaves no track. It just loads to the memory, and after you're done with it, it will just get removed from the memory. And main reason the Kali became popular is like a well-known penetration and forensic tool. So as in penetration tools, our other team members going to talk about this in detail. But what I was usually using this was for back in like a 2014, something like that. I can't remember right now, maybe 2010. The Wi-Fi password was based on VEP technology, and VEP security protocol isn't that secure at all. And you can actually use this WebNG, NGTrack, that kind of tools to sniff the Wi-Fi hotspots around you, and you can check the traffic coming and going out in the between, and you can go in between and see if there's a password in it, and you can get a password from it. And it was really, really useful when you hadn't had any kind of internet connection in old days. So like basically I was able to get into somebody's Wi-Fi location, Wi-Fi hotspot using this CD. It was really useful. And another thing was like you can check if the computer has infected or not using those kind of tools as well. And yes, you can load your whole operating system. Like that means that you can load your hard drives into that, and you can clean that hard drive from any kind of malware stuff, and you can actually fix the other like operating system that is resides on the hard drive, and you can add more tools if you like. So the downsides of Kali is it's usually really slow, and it is based on the USB drive, so we can't expect a speed from it, but it can do what it should be doing, and it is usually read-only mode. But the modern versions nowadays has its own partition that can be dedicated to storing information as well. But if you had this CD-ROM version, so there is no way you can write into the CD-ROM anyway, and that was like a whole main point. And since you already have this one version on the CD or USB, there's no way to update or upgrade the things. So it was that's like a kind of annoying, because usually there's a new version comes out in a frequent manner, and if you want to have the up-to-date technology, up-to-date operating system, you had to burn it to the CD every time, or you had to write it to the USB stick all the time. I think it might have changed now. I'm not completely sure. And back in the very old days, if it's like very old mainboards, those couldn't load from the USB or CD-ROMs, so that was useless. So yeah, I'm talking about like a really old computers, which is like a 486, something like that. It wasn't like if you want to do something on those computers, you actually had to have floppy disks in order to boot from those. And yes, as I told you before, you have to write a new version every time. So yeah, this is my whole slide. I think it just closed itself. So my other team members gonna go through this in detail, and hopefully, yeah, they will do a better job than me. Okay, so that's it. So anybody here?
So any questions from anyone?
I don't think, can you hear me like a better way?
Yeah, I can hear you.
Oh, okay. So yeah, that's it.
Yeah, just a comment with the live USB. You can update it and stuff now. You just have to go into the persistent mode, because it does have a little partition on the USB drive that saves stuff. So you just go in there and you do all your updates and stuff in there, and it saves it for when you're using it in non-persistent mode.
That's great. Yeah, I haven't used Kali for a while now. It's just like my kind of memory that I had with it. And I was using it as a backtrack very long. Backtrack was like a crazy thing back in the day. Like if you heard and know about the backtrack, you were considered as a hacker.
So we did have one question from Bailey.
Mm-hmm.
Can you see it?
So I think other people, like people has the preferences. In my opinion, I don't really want to use any kind of operating system on the computer except it's Ubuntu or CentOS. So the main reason for that is just that's my personal preference, because all the other operating systems has its own problems and issues. So you have to deal with all of these. So if you go with a general like branch, which is Ubuntu or CentOS, those are like a really stable, and it will work for most of the computers without any issue. And if there's an issue, there's usually a solution for that on the internet. So I don't think it is beneficial to install Kali on the HDD, but you can install it as in like your main operating system. But I would definitely recommend to use like main operating systems like Debian, CentOS, or Ubuntu. And that makes things way much easier when it comes to setting up the virtual environment or like a server environment. Then you will be actually the same. You're going to be actually the same branch on the same operating system. So if you want to use Ubuntu, like a Linux operating systems, like people has the preferences, but I would recommend to use Ubuntu if you want to have Unix kind of branch. If you want to have Linux kind of branches, I would recommend to use CentOS. And those two are like a main operating system for servers right now, and you will get much more familiar. But yeah.
Yeah, the only thing I can see is that if you had a computer that is dedicated for penetration testing, is a reason why you would have it on a hard drive. Other than that, like you said, there's other operating systems that are better.
Yes. Thank you. Okay. I don't want to be yelling like you have to. So, and then.
I'm still muted. So anyway, I hope you can still hear me. Can you still hear me? Hello?
Yes.
Okay, good.
Yeah.
So every once in a while, my mic will mysteriously decide to turn off. So yeah, next up, I believe, is Josh. Is that correct? And then Jacob will close us out. Is that correct?
Other way around.
Okay, Jacob and then Josh. Okay, great. And then next will be Jessica with a Haiku operating system. So we have our Chapter 4 programming assignment that's due by midnight tonight. And we will continue now on Chapter 6. Okay. So actually, I have it highlighted in red that you are seeing my presentation. Is that correct, or do I need to reshare it?
Can see it.
Good.
I can see it.
Oh, good. All right. So this is the slide that we left off last time. It was in terms of the source job first, and basically the way that is generally done is through assigning priorities based on the length of the job or the amount of the time that's left. And so the source job first then becomes a priority scheduling schedule where the priorities are set based on the amount of time that is left for that process to do. We talked about how starvation can be a problem with this scheme because it is possible if you're a long enough process for you never to get enough time. And the solution to that is aging, where as time progresses, your priority gets constantly bumped up by a monitor thread that notices that you've been there for a long time, and your priority gets bumped up. So that's a key thing to remember, is that there is a solution for starvation, which is aging, where your priority is bumped up as you age. Let's see. Okay. I thought I skipped a slide. So the next one is round robin. Each process gets a small unit of CPU time called a quantum. And then it just sequentially goes through all the processes that are waiting to run and gives them their quantum period of time to run. So if there are n processes in the ready queue and the time quantum is q, then each process gets 1/nth of the CPU time in chunks of at most q time units at once. So no process waits for more than n-1 times q time units. Timer up every quantum to schedule the next process. So key things are here is if Q is very large, your quantum period of time is very large, then it becomes very closely looking like a FIFO queue because you would think that if the large quantum, that most processes, or a lot of processes, would be actually be able to run to completion. So then it becomes a first in, first out. Now on the opposite side, if the quantum period is too small or is small, then the overhead becomes extremely high because you're spending all your time doing context switches, which is bad. You don't want to spend all your time doing context switches. You want to be able to actually spend the majority of your time actually doing the activities that the process wants to accomplish. So those are the two extremes, and those are the trade-offs that you need to consider. So the quantum time should be large with respect to the context switch time. Should be large because, again, you don't want to spend all your time doing context switches, so you make it larger than your context switch by a considerable margin. So here's an example of the round robin with a quantum time of 4. And you can see here's the chart of the process 1, 2, 3, 3, 1, 2, and then 1, 1, 1 as we finish up, because the process 1 has a time of 24 that needs to accomplish, and P2 and P3 have a quantum time of 3 units that they need to use. So you can see that process 2 and process 3 are able to finish their job as soon as they get access. Basically, the quantum time is 4 and they only need 3. They are able to completely finish during their quantum time. The average turnaround time is greater than shortest job first, but is more responsive. You don't have the situation where a task is getting starved off. Again, Q should be large compared to the context switch time. Typically, the quantum period is 10 to 100 milliseconds, and with a typical context switch of about 10 microseconds. So again, notice the difference in units that we're using. We're talking about milliseconds, 10s to 100 milliseconds, versus the context switch of 10 to the minus 6 or microseconds. So again, a significant difference between the context switch time and the quantum time. Yes.
Process finishes before its context time, or the quantum time, does it still use that, or is it on?
No, it immediately gets switched out because you basically have relinquished your control of the CPU at the end of the process. So if you see here in the Gantt chart, the P1 takes its 4 things of quantum time, then P2 takes only 3 of the quantum time period, and immediately process 3 then jumps in at timestamp 7 and then takes from 7 to 10 with its 3 units, and then immediately P1 at timestamp 10 gets control. So you would relinquish your control of the CPU if you've already finished before your quantum period is up. So that is a good question, but yes, you would want to maximize the usage of your CPU, and that would be to release it before your quantum time if you are done. Any other questions? All right. Here, this is the time quantum and the context switch time. And so you have process time and the number of quantum switches. So we have one quantum 6 switch, and then on the example on the bottom, we end up with 1 quantum and context switch is 9. So again, this is something that you need to look at with round robin, is what the time difference between your context switch time is and your quantums as you look forward. The other technique is actually a multi-level queue, and that is combining multiple techniques for scheduling. The ready queue is partitioned into separate queues. For instance, a foreground or background. So background could be batch processes, and the foreground could be interactive, and you would give priority to the interactive in that case. And then we have processes permanently given a queue. So each process gets their own queue if in the case where it's like multi-threaded or something like that. And then we also have a situation where the queue could be round robin for one, and the first come first serve for another, or shortest time first. So you can actually have queues that use different scheduling algorithms, and then something that would schedule between the different queues. So the last slide basically says that we have to have some scheme between scheduling between the queues. So fixed priority scheduling, that you give more to the foreground task and less to the background. But then again, you have to manage the possibility of starvation, where actually a whole queue might be result in having starvation issues. So again, we're just creating extra levels of scheduling granularity and techniques, but at each level, we still have to consider the possibility of starvation. So you can time slice. Each queue gets a certain amount of CPU time, which you can schedule among its processes. And so, for instance, 80% to the foreground in round robin, and then 20% to background in first come first serve, for instance, for this example. So again, this is a hybrid technique that can be used. The other thing is a multi-level feedback queue. A process can be moved between various queues based on their age, for instance, aging, or from other criteria where the processes are moved between separate queues, as opposed to that first slide where it says each process is permanently given a queue. In this example, we are allowing, based on various feedback or various information that you discover as you're scheduling, that you can move processes between different queues. And that's the slide here basically goes over some of the different things you have to consider when you're doing a multi-level feedback queue. So these are things you need to worry about, is how to upgrade, demote, etc. So thread scheduling, there's a distinction between user level and kernel level threads. Certainly, you are going to give priority to kernel level threads because they are doing critical trusted operations that you want to behave efficiently. When threads are supported, threads are scheduled, not processes. So again, we talked about how Linux, a thread and a process are one and the same. They're one-to-one. So there are various models of how you handle threads to processes, and we talked about that, I think, in an earlier chapter. We have the one-to-many and the many-to-many models of handling threads, which is the mapping between threads and processes. And then we have the concept of a lightweight process and heavyweight processes. And then we have this concept of process contention scope, which is competition within a process where there's competition between the threads for a given process. And it's typically set by priorities set by the programmer for handling that contention. Kernel threads are scheduled onto available CPUs in system contention scope, competition among threads in a system. So overall, that the kernel will be the one that determines which threads get priority. So user level threads are managed by a thread library, and the kernel is usually unaware of the thread management. It's up to the process to do it. User level threads must ultimately be mapped to a kernel level thread to run on a CPU. And this is our mapping processes and threads. So again, we have the various models, the many-to-many and the many-to-one and many-to-many, and some of the other ones which we actually had hybrids as well. But those all apply here. We have an example from your text. I won't go into it in a great detail, but it talks about the API for pthread scheduling. So this is for the standard pthreads, and you can look at that in more detail in the text. And it can be limited by the operating system. Linux and Mac OS only allow pthread scope system, whereas the API allows pthread scope system or pthread scope process, which the process so basically it's whether the system or the process does that. But certain operating systems limit your capabilities to only allowing the system to affect the scheduling. So then we go on to multiple processor scheduling, or also multi-core would be the same case. So the scheduling gets a little bit more complicated because now we have multiple places, not only multiple threads and processes that need to run, but we also have multiple CPUs essentially that can handle those processes. So we have the homogeneous processor model within a multiprocessor, which is basically all the processes and threads are assigned to each of the different cores or processors homogeneously, as if they are all treated the same. We have asymmetric multiprocessing, where there is a preference given to various certain processes are given preferences to go on a specific processor, either one or multiple. And then we have symmetric multiprocessing, where they are all treated the same. Processor affinity is when a process is given affinity for running on a specific process. So it's my preference that I'm stating. And oftentimes that will happen when a process runs on a particular processor. It may then establish that there's an affinity to come back to that same processor for whatever reason. For instance, the cache memory that has stuff in the cache memory for that processor or that core, and we want to come back to it because it will avoid having to move information from one cache to another. So when multiple processor scheduling system supports hard processor affinity, a process can specify a subset of processes that they want to run on. So you can actually say, only processor 2 and 3. I don't want to be on processor 1, things like that. You can give a set of processors. That's the processor set idea. And then soft affinity tries to keep the process on the same processor, but gives no guarantee. So soft says there's no guarantee that you will be giving your preference. You may be allowed to give a preference, but there is no hard and fast rule, as opposed to hard affinity, where you are, when you give your preference, you are given your request is fulfilled, that they do use your request and adhere to your request. So here is something that I did allude to, and that is with non-uniform memory access, in particular with caches, that there will be slow access if you're trying to access some other CPU's cache memory, or any other memory that has faster processing from one CPU versus another CPU. So that's something to keep in mind, is we do have non-uniform memory access performance situations where certain hardware is easier to get to, memory hardware is easier to get to from one CPU than another. So when we have multiple processors, we have to worry about load balancing. You don't want one processor to be tied down completely, whereas another one would be basically having all kinds of slack time. So load balancing attempts to keep the workload evenly distributed. There's two techniques. One is push migration, where a task periodically checks to see if the other CPUs are available and will move itself, or pull migration, where the auto processor will go out searching for processes that are in the ready queue and take them and grab them and put them in their run queue. So there's push and pull techniques. This applies if each CPU has its own ready queue only. You can imagine that one technique would be to have a single ready queue that all the CPUs pull from, and that would be in the symmetric case where all processes are taken evenly. So that would be a single queue. And then sometimes the push and pull operations can be done in parallel, which provides advantages. So again, remember that there are two techniques that we can do load balancing with multi-processor systems. That's the push migration and the pull migration. So current trends for multi-core processors is to place multiple processor cores on the same physical chip. That's the multi-core. The advantages are it's faster and consumes less power, and multiple threads per core also are growing. So it takes advantage of memory stall to make progress on another thread while memory retrieve happens. So here we're getting the situation where not only are we able to swap out and utilize the CPU when a process is waiting for I/O from a disk, for instance, but also when we are waiting from the response from memory to give even faster performance, that we're able to, while a task is waiting for access to a memory, another process can be swapped in to do some work. So here is an example diagram of an example of multi-threaded, multi-core systems where we have multiple threads, and then we have compute cycles is C, and memory stall cycles are M. And we can see here that with a single core and a single thread, we have just interleaving compute, memory stall, compute, memory stall. And we can see here that we have multiple threads. We can now interleave thread 0 and thread 1 to take advantage of the memory stall times. So another interesting case is the situation with real-time programming. It can present obvious challenges, real-time systems do. And so there are two basic types of real-time systems, soft real-time systems, where you're trying to run quickly, but there's no guarantee is when a process will be scheduled and completed, in particular completed. Whereas we have hard time real systems, and the definition of a hard time real system is the task must be serviced by its deadline, that and a deadline has been established, and if that process is not able to complete its task in the deadline period, really bad things will happen. And I know that in particular that applies to motion control systems for manufacturing machinery and robots, where you're given a command on a periodic basis of the next location to go, and it is really bad if the process does not complete within a given time because there are time intervals where a new position update needs to be specified, and if you miss it, tragic things can happen in a lot of cases where robots can crush something or go past its limits, those kinds of things. So that would be an example of a hard real-time system. Two types of latencies can affect performance. Interrupt latency, that's the time of the arrival of an interrupt and the start of the interrupt service routine. And then dispatch latency, and that's the time, the latency it takes to schedule the current process and switch it in, or do a context switch into the CPU. So that's the interrupt latency and the dispatch latency. Here we have a diagram of that concept here. You can see here that you have the interrupt processing and we have the dispatch latency, which can be, the dispatch latency can be characterized by the conflicts with other running processes, and then the actual time it takes to do the context switch or dispatch the new process. And then real-time processing occurs. So for real-time scheduling, it is typical to have your scheduling of processes to be dependent on the priorities of that particular process. You have the hard real-time processes that will have top priority, and then you will have processes that have less of a hard real-time component to them, and they will be lower priority tasks. So processing have a new characteristic, which is a period, which is the period of time that it needs to run to meet its next deadline, and that's the period. And the frequency would be the inverse of the period, which is here the rate or frequency, which is 1/p, and that's you'll hear of hertz and megahertz. That's what we're talking about. We're talking about the rate. So one very common technique for scheduling a real-time system is rate monotonic scheduling, where a priority is assigned based on the inverse of its period. So here we have shortest job first, basically popping up. It's basically that same technique. Shorter periods have higher priority and longer periods have lower priority. And so we have here an example of P1 and P2, with P1 having a shorter period, and so it is given priority. Another scheme is earliest deadline first. Here we're taking advantage of a task knowing when its deadline is. And so we say any task that has a deadline that is first, that needs to get their job accomplished, is given priority to scheduling into the CPU. So that's earliest deadline first. Going back to the rate monotonic, we'll kind of discuss this versus some other algorithms. Oh, that's an old alarm. It says it's time to pick up my grandson, but I know he's with my wife. So anyway, rate monotonic scheduling is considered optimal, that it optimizes the use of the CPU. And it can be, there can be a nice, easy algorithm for scheduling the priorities for each of the tasks. The limitation is CPU utilization is bounded. That is, utilization goes down as the number of processes go up. So as you if you have more and more separate processes or threads, all of a sudden your usage of your CPU goes way down. And so we can see here in this diagram that around 80 to 100, we see that the CPU is not being utilized at all. So that is actually an unfortunate characteristic of rate monotonic scheduling, is that as you get more and more processes and threads involved, all of a sudden the utilization of the CPU goes down. And then keep in mind again that the task with the shortest period will have the highest priority in the rate monotonic scheduling. With the earliest deadline first scheduling, it's theoretically most optimal for meeting schedules. However, it's still limited by CPU usage due to context switches and interrupt handling. So we do have our overhead factors. And then the text talks about proportional share scheduling in POSIX. We won't go into it in class, but that's in the text. And then it also does discuss more information about choosing the most accurate or the best algorithm. So keep in mind when a process becomes runnable, it must announce its deadline requirement to the system in the earliest deadline first scheme. Deadlines are assigned as following: the earlier the deadline, the higher priority; the later the deadline, the lower priority. So again, it is tied to the priority is tied to the deadline as opposed to about how long it's going to take in the shortest time first or the rate monotonic scheme. All right, so that concludes our time, and actually it concludes our slide for this topic. Any questions? So that was a pretty quick class. So any questions about, again, the lecture or anything regarding the class or the scheduling of topics? I am noticing that as we go online that not only are the assignments need to be adjusted in terms of their due date, but actually there was a case in my software engineering 1 class where the context of what was being asked for was beyond what I was now going to be asking for as we've gone online. So any questions? Otherwise, you're free to leave. You're dismissed, and